Hello everyone, welcome to another exciting edition of Statistics 100. Right now we are doing section 8.5 from the textbook, that is estimating the difference between two population means. So in this section, things are a little bit different from the previous section, and I'll explain exactly how right away. So here we have two populations, and so we're going to call them population 1 and population 2. And that can be men versus women, for example. Suppose we are looking at prevalence of, no, forget that. Suppose we are looking at heights differences, and so we want to see if women are shorter than men, for example. Then we might have two populations of men and women, and we would have a different population mean for each population. We would also have a different variance and a different standard deviation. Another way we can get two populations is if we have different treatments for two populations. So for example, if we have a garden and we are trying out a new pesticide, we might compare one pesticide with another pesticide. So we would have population 1 would be treated with the first pesticide, population 2 with the second pesticide, and that would again make two different populations. So for each population there's a population mean. As always, we use the letter mu for the mean. However, we introduce a subscript to separate or to distinguish population 1 from population 2. So population 1 has mean mu sub 1, and population 2 has mean mu sub 2. And we also have a variance. As usual, the variance is represented with the symbol sigma squared. And again, we decorate the variance with a subscript to indicate which population it belongs to. Sigma squared sub 1 for population 1, sigma squared sub 2 for population 2. And of course we have standard deviation, and that is simply the sigma without the square symbol. So sigma sub 1 for population 1, sigma sub 2 for population 2. So those are various parameters. And of course, I should mention that we are dealing with a continuous case here. So we're talking about measuring. There's also a discrete version, which we are not covering in this course. So when we're talking about the difference between two populations, we are only talking about population means in this course. Okay, so those are parameters, and we also have, of course, we can take a sample from each population, and that gives us statistics. So we have population 1, we can take a sample from it, sample 1. And population 2 has sample 2. So we can have, for example, the sample mean, and that will be x bar. But we're going to decorate it with a subscript of 1, x bar sub 1 for the mean of sample 1, x bar sub 2 for the mean of sample 2. We have a variance, a sample variance. We use the letter S for sample variance, S sub 1, or S squared sub 1 for the sample variance of sample 1, S squared sub 2 for the sample variance of sample 2. We can have standard deviation, and those are just S sub 1, S sub 2 for the respective samples. And in the case of a sample, we have the sample size. And that is usually denoted by the symbol n, but in this case we're going to decorate it again, once again, with this index, n sub 1 for sample 1, n sub 2 is the sample size for sample 2. So these can all be different. The sample sizes for the two samples can be different. The sample means will be different in general. The standard deviations and the variances will be different. One last reminder about this: in this chapter 8, we're talking about large samples, and so that means that both n1 is bigger than 30 and n2 is bigger than 30. So both of our samples are large, have to be large in order for us to use the techniques of this chapter. Okay, so what are we going to do with this situation? Well, it turns out that the central limit theorem can apply to this quantity. So normally we apply the central limit theorem to the mean, but if we have two populations, it turns out that we can also apply the central limit theorem to the difference between the two means. And you know, the exact mechanism for this is something that we're not going to talk about. But rest assured that the mathematics is solid, and it's actually not that much harder than the central limit theorem for one population. But we're not going to go into the proofs or the exact mechanics even of how to apply the central limit theorem. So you should just take my word for it that this is that it actually does apply. The central limit theorem in this case says that the mean of this quantity, x1 bar minus x2 bar, is normally distributed, approximately normally distributed, and of course I have to give the mean of this quantity and its standard deviation. The mean is going to be, as you might expect, the difference between the two population means. And the standard deviation, which we call the standard error, just to avoid a certain amount of confusion that can occur, has a nice formula. Sorry, I'm going to patch this up a little bit. There. First I'm going to put the sigma 1 squared divided by n sub 1 plus sigma 2 squared divided by n sub 2. Then I'm going to take the square root of the whole thing. So that is what the application of the central limit theorem to this situation tells us that the quantity x1 bar minus x2 bar, the difference between the two sample means, in other words, is approximately normally distributed with mean mu1 minus mu2 and standard deviation, which is called standard error, being equal to this rather more complicated expression. This is one of the most complicated expressions we're dealing with in this course. This course is the kind of algebra that we deal with in statistics is fairly simple. This is the most complicated expression we're going to be dealing with. And the thing to note about it is the correct order of operations. So the correct order of operations means we take these quotients first, then we add, and then we take the square root last. So you have to do the operations in that order to get the correct result. You can use brackets on your calculator to calculate this thing. And if you don't like using brackets on your calculator, then you're going to have to write down some intermediate results on a sheet of paper. Either way is fine with me. But just note that this is probably the most complicated expression that we're going to be dealing with. Okay, one other issue about this, as usual, for a large sample, meaning n sub 1 is bigger than or equal to 30, n sub 2 is bigger than or equal to 30, we have, in that case, that sigma 1 is approximately very close to S1, and sigma 2 is very close to S2. So we can approximate SE by this expression. Oops, and so 2. In other words, we take the correct value for SE and we replace the sigmas with S's. And as usual, that's because sigma is inaccessible to us. We do not know what sigma is. But however, we do know what S is for each sample. We can calculate that because we have the sample. And because the two values are probably very close to each other, we're going to substitute one for the other. That's not entirely 100% correct. However, it is a reasonable approximation that is shown to be acceptable. So, for acceptable for a large sample. That is really all that we need to know in order to make this work for us. So next thing we're going to talk about is standardizing this distribution. So this is a normal distribution, which means it can be standardized. And the usual process for standardization applies. In other words, we can calculate a z-score, and that is the measured value of the difference minus the theoretical population value for the difference. And we divide that by the standard deviation of our distribution, which in this case is the standard error. And we're just going to slip that approximation in. There. And so this is the z-score for this approximately normally distributed random variable x1 minus x2. And this will enable us to solve problems using or applying to the difference between two population means. This, by the way, is another statistic. I think I forgot to mention that these are all, of course, statistics. Meaning that they are based on a sample. That's all that we mean by a statistic. These are based on samples, whereas parameters are based on the population. So the sample mean, the sample variance, the sample standard deviation, the sample size, these are all statistics. And similarly, the z-score in this case is also a statistic. So it's called sometimes the Z statistic for this distribution. One other important thing to note about this is that in some of these problems, in some of these sections of Chapter 8, we have been using the standard deviation. Let me just write this for standard deviation. And in this chapter, in this section, we tend to use the variance more often. So the difference is the standard deviation doesn't have the squared symbol, whereas the variances do have the squared symbol. And it's just more convenient to express the formulas in terms of the variances, because that is how they appear in the formulas. So the variances are in the standard error formula for the difference between two population means. Compare that to a single population. The formula for standard error looked like that, and that was based on the standard deviation. In this case, it is based on the variances. Oops. So that's something to be careful about. It's a potential source of error, is that when a problem gives you variances, you may misread that as a standard deviation and then go ahead and square it a second time, and that would be a mistake. So keep an eye out for that. If a problem says that the variance is 12, for example, we would write that as squared is equal to 12. And if the variance for population 1 variance is 12, then we would write that as squared sub 1 is 12. And that would mean S1, S1, I'll probably erase that blob. There we go. That would mean that S1 would be the square root of 12. Okay, so keep an eye out. Does our question talk about variances, or does it talk about standard deviations? And use the appropriate formula. All right. So in the case of the difference of two population means, we want to do a point estimator is the first thing we're going to do. Point estimator for mu1 minus mu2, and that is, of course, x1 bar minus x2 bar. So if you are running a cheap magazine and you're talking about the difference between the heights of men and women, then you're going to estimate the difference between the average heights of men and women as the difference between the average heights of two samples. And if you're writing for a cheap magazine that has not got any kind of scientific reputation, you would just stop there. But as I emphasized in a previous lecture, that's not a good place for us to stop. That's not why we are learning statistics. We're learning statistics because we are learning to appreciate the importance of the margin of error concept, the standard deviation and the corresponding margin of error concept. So the 95% margin of error, as usual, is going to be plus or minus 1.96 times the standard error. And if we change that 95 to something else, we're going to change the coefficient 1.96 to something else. Okay, now that is the point estimator margin of error business, but a more sophisticated way to talk about it is to use confidence intervals. And so the 1 minus alpha 100% large sample confidence interval for the difference between two population means is given by this formula. It essentially is just combining all this stuff together. X1 bar minus X2 bar. That is the point estimator plus or minus the margin of error. The margin of error comes in two parts. The standard error times the Z sub alpha over 2 value, which is exactly the same as it was in the previous section. Z sub alpha over 2 depends on alpha. Alpha is the quantity which depends on the confidence level, and we call alpha the significance level. So for the usual table, for 1 minus alpha is 95%. I'm going to write it like this just to be consistent with the textbook. So suppose 1 minus alpha 100% is 95%. Then alpha is 0.05. Alpha over 2 is 0.025. And Z sub alpha over 2, which I showed you how to calculate, is 1.96. And 90% confidence corresponds to 10% significance. Alpha over 2 is 5%, and Z sub alpha over 2 is 1.645. Should be familiar to you from the previous section. If we're looking at 98% confidence, alpha is 2%, alpha over 2 is 1%, Z sub alpha over 2 was 2.33, and for 99%, alpha is 1%, alpha over 2 is 0.5%, and Z sub alpha over 2 is 2.58 by convention. We could have more decimal points there, but we conventionally don't. So these are the numbers that you'll find on your formula sheet. And these are the numbers that you should use when you try to solve one of these problems. And this table is exactly the same as it was in section 8.4. So it's always going to be the same. For chapter 8, chapter 9, we're going to repeatedly use this table, which is why I put it into the formula sheet. It's very important. And when you do enough of these, you end up just memorizing these numbers. But for now, you can refer to the table in the formula sheet. And of course, you can always calculate these numbers on your own by reverse lookup. You reverse lookup these numbers in the Z table, and the Z value that appears on the edge is this last column. So there's many different ways you can obtain this table, but the easiest way is just to look it up on your formula sheet. All right, so that is really it for this. That is almost all there is to it. So we're going to take a look at a couple of problems. There's one more little issue, but I will look at the problems first, and then we will talk about this final additional issue. So you can take a look at the problems in the textbook. They're both good. I recommend you read them both. So one of them is about comparing two types of automobile tires, and the other one is about comparing dairy intakes, daily intakes of dairy products. So for comparing men and women, how much dairy products men eat versus how much women eat. So those are both good examples in the textbook. I'll let you read those in detail. I want to do another one. So we're going to take a look at hotel costs, and I think I'll have to come back and finish this off in a few minutes. So I'm just going to close this video while my furnace starts up. It's going to make a lot of noise, so I'm just going to wait till the furnace is finished before I record the second half. All right, see you soon.